Hi everyone. This is Dr. Venkateswarlu, working as a professor of EC at IARE Hyderabad. Today we will be discussing about elementary signals. The elementary signals, it is followed by exponential signals, sinusoidal signal, step function, rectangular pulse, impulse function, and derivative of the impulse, and ramp function. We will verify these all elementary signals one by one. So here, by using this all elementary signal, we are able to estimate that signal analysis and what is interlinked with these signals and system. For this, so elementary signals here, exponentially signals we have to consider. So from this, the exponential signal, it is followed the exponential signal, it is followed by x of t is equal to b into e power at, where it is b and a are the real parameters. Okay, so for here, decaying the exponential for which a less than or equal to 0. Okay, if growing that exponential for which a greater than 0. So easily can estimate that exponential signal. So for here, t versus the time versus x of t, where x of t, t versus time versus x of t, easily can analyze that the time is from 0 to 0 0.1, 0 0.2, 0 0.3, 0 0.4, 5, 6 up to 0 0.9 and 1. So in x of t, from origin to 0 0.5, 1, 1.5, 1.2, 1.3, 1.5 and 2.5, 3 and so on up to 5. Easily can estimate that what you call it is decaying the exponential for which a less than 0 and growing exponential for which a greater than 0. Here. So from here, this both decaying the exponential for which a less than 0. So from t versus and x of t, and growing the exponential for which a greater than 0, where here the t versus x of t. So go on using that initially that origins to 0 to 1 here from this. So easily right to verify that what do you call this graphical representation. Okay, for this, this is followed by decaying the exponential form. These are the decaying exponential form of what you call continuous time signal. Where if it is growing, here it is growing exponential form. If it is a continuous time signal. Okay, with this the exponential signal. Signal exponentially signal x of t, where what do you call that x of t, where x of t is equal to p into what do you call e power at. Okay, like this, b and a are the real parameter. So here if it is a less than 0, decaying the exponential for which, if it is a greater than 0, growing the exponential for which. So user can verify that how it is growing, how it is decaying the exponential form of CTS, continuous time signal, and growing the exponential form of CTS, continuous time signal. Okay, like here, so if you want to consider this loss capacitor, so if you want to apply this, consider this circuit, the capacitor is R, where you want to calculate the I of t is C into d by dt into V of t. Okay, consider this one, loss capacitor. So using this figure, apply the KVL, where RC into d by dt, Vt of t equal to 0. Okay, so from this, if you want that V of t, so where V of t is equal to V0 into e power into RC. If it is where RC is the time constant. So with this loss capacitor, consider this loss capacitor with the with the loss represented by the shunt resistance R. So with this the loss capacitor where RC time constants, it is loss capacitor with the loss representation of the shunt resistor. So similar to the discrete time case, if we are using the discrete time cases, we know that continuous time signal where what do you call x of n, where x of t or x of n, if we are this is all nothing but what you call continuous time signal. Coming to the discrete time signal, this discrete time signal x of t, okay, or you can consider that x of n, if it is a discrete time signal, where here it is, this one nothing but a discrete time signal. Here we should consider that where discrete time signal x of n is equal to b into r power n. So where r is equal to e power alpha. So we have to consider that with reference to this, you have to design that what you call the t versus x of n. Where previously we have mentioned that x of n or x of t is the continuous time signal. Consider here that what you call discrete time signal where x of n versus the time n versus x of n. So to verify the discrete time cases. So from here within this, so it is graphically it is represented using this solar within this, okay, that n, okay, that n time n. So n is initially that origin is 0. From here 0 to here it is this case minus 2, 4, here it is minus 4, here it is 6, here is minus 6, and 8, here it is minus 8, and 10, here is minus 10. With this the time n is specified. So with reference to time n versus that continuous discrete time signal where DTS, discrete time signal. So reference to this where discrete time case where x of n is equal to b into r power n is equal to represent this, okay. So where it is from this, these are the decaying exponential form. If you are using this discrete time cases, this is all nothing but what you call this figure is followed by decaying exponential form of discrete time signal. Decaying exponential form of DTS, discrete time signals. Coming to this case, the exponential form of discrete time, it is growing from here to here, it is growing, okay, this growing with the help of this, under this growing what you call exponentially, okay, growing that exponential form of what you call discrete time signal. Previously we have verified that continuous time signal. Now it is a discrete time signal where discrete time cases where x of n, it is all relevant to this, where x of n is equal to what you call b into r power n, okay, like this. So the discrete case, you have to use this one where r is equal to where r is equal to what you call e power alpha. Like this, you have to verify in graphically. Okay, next elementary signal, that exponential, if it is in terms of the what do you call mathematical expressions, where x of n is equal to b into e power a into t, where a less than 0, okay, and from time t versus what we call that continuous time signal x of t. So it is various. So here from this, from origin 0 to 0.1 and up to 5, 6, 0.8, 0.9 and 1. from this here in y-axis, the continuous time signal is for the x of t or exponential signal, where x of t is assigned from 0 to 0.1 to up to 5. In between that 1, 1.5 to 2.5, 3.5 up to 5. Like this, where x of t is equal to b in t power 8 or what you call t a. Here it is a less than 0, but this case a greater than 0. So from this, so we have to verify that graphically the time t versus that time t versus the x of t. This is the exponential signal, or when we consider continuous time signal. So here it is. We can consider this all like this, where x of t is equal to a into e power alpha t sine of omega t plus pi. Here, where alpha greater than 0. Okay, so we can consider where t versus what you call x of t. Now it is verifying that x of t value. Next, under this, yeah, and the elementary signal, what are they? So if you want to analyze this all elementary signals, we require that signals, how this varies, how many signals are available, what is the variation with this all elementary signal is affected about the time you are concerned. A signal is a function of one or more independent variables that carries some information to present a physical phenomenon. Okay, a continuous time signal, like in terms of this, where CTS, continuous time signal, also called as log signal, AS. It is defined along with the continuum of the time. Okay, here it is in terms of graphical t versus x of t, where continuous time signal is following x of t. Okay, so it is where x of t is equal to a into e power at, t greater than or equal to 0. So this, a signal is a function of one or more independent variables that carries some information to represent a physical phenomenon. A continuous time signal, also called as log signal, is defined along a continuum of the time. Okay, a discrete time signal. Previous one is it is what we call CTS, continuous time signal. Coming to this, present one is that is discrete time signal. A discrete time signal is defined as at discrete times. Okay, here like this, n versus x of 0, here from origins to here x of 0, x of 1, x of 2. Okay, here it is x of 0, because of it is the continuous time signal. So discrete time signal is defined at discrete times, x of 0, here it is x of 1, okay, x of 2. X of is a discrete term. Where it is a continuous time signal, it is followed, we write to represent x of n. Okay, come to the discrete time signal, we have to verify that x of it is represented with x of n. Okay, so like this, where n versus x of n. Okay, here x of 3, x of 3, x of 4, and x of 4, x of 5, and so on. Okay, so in this side 0, minus 1, here x of minus 1, here x of minus 2, here it is x of minus 3, okay, x of minus 4, x of minus 5, and so on. Okay, so we will represent this discrete time signal is defined at discrete times. Come to the elementary signal, sinusoidal or exponential signals. First of all, we are ready to involve that enter into the sinusoidal or exponential signal. The sinusoids and exponentials are important in signal and systems analysis because they arise naturally in the solutions of the differential equations. Okay, So sinusoidal signals can be expressed in either of the two ways. One is cyclic frequency form, other one is radian frequency form. In the cyclic frequency form, so easily you can represent in terms of the mathematical notation, like here, where it is a sine of 2 pi f naught into t is equal to a sine 2 pi f naught t is equal to a into sine 2 pi t by t naught, where here that a sine omega naught t and omega naught t, we know that omega naught t is equal to 2 pi f naught. It is also, we can consider it is also equal to 2 pi by what you call t naught. Here we know that where t naught is, it is specified that t naught is nothing but a time period of the sinusoidal wave. Time period of the sine wave. Here, the sine wave, sinusoidal signal is, you can consider time, continuous time. Okay, x of t is equal to a cos of omega t plus pi. We can consider it mathematical expression for this. For this case, we require that figure in terms of this graphically. The graphical representation of this, what you call t time t versus what you call x of t, continuous time signal. It is specified the continuous time signal is followed by CTS. CTS, continuous time signal, it is followed by this x of t, where x of t is equal to a into cos of omega t plus pi. Okay, from this, graphically it is available that graphical representation of this mathematical notation will appear that where time versus x of t. Okay, so where that if it is time, where the t is equal to 2 pi by omega, it is, can combine this vertical periodicity. Here in this case, x of t plus capital T is equal to a into cos of omega t plus capital T by pi, where a cos, we can simplify this, a cos omega t plus omega t, this both are plus pi, and a cos of omega t plus 2 pi plus pi, and a cos omega t plus pi, where you can consider it is x of t, where therefore that what you call x of t plus capital T is also equal to that what you call x of t. Like this, it will specify. So from this, where x of t, if the sinusoidal a cos omega t pi with phase pi is equal to plus pi by 6 radians. Okay, it is specified that, okay, it is specified that graphically like this. Okay, if it is sinusoidal signal a cos omega t plus pi, okay, with phase is pi, what you call pi by 6 radians. Okay, so here you can consider t versus continuous time signal x of t. Okay, like this it is specified. The next generation of the sinusoidal signal, we would consider the circuit with the help of inductor, this capacitor, both are connected. From this, we need to apply that V of t here. Okay, after applying here, easily can ready to calculate the current. Okay, the current I of t, where I of t is equal to, because of we are in the capacitor, C into derivative of that capacitor, d by dt into that input voltage like V of t. Okay, so using this all, consider this circuit is what is the generation of, it is the generation of a sinusoidal signal. This is generation of the sinusoidal signal, it is specified. So from that circuit, right, calculate that L and C because of this inductor and capacitor combination of these two. It is specified here that LC with the derivative of d square by dt with the input voltage plus Vt of t equal to 0. So we want to calculate V of t. V of t is equal to V naught of cos omega t into t greater than or equal to 0. Where omega naught, we want to specify this omega naught, where omega naught is equal to 1 by square root of L and C. This is specified the natural angle frequency. This is all our omega naught is nothing but the natural angular frequency of oscillation of the circuit. Because of we have considered this all a parallel LC circuit, assuming that the inductor L and capacitor are both ideal case. This is related to the generation of sinusoidal signal with reference to circuit diagram and mathematically, where the natural angular frequency of the oscillation of the circuit will be reflected. Yeah, this is related only sinusoidal signal. Yeah, coming to this discrete time case. Okay, in the discrete time case, it is followed. If it is discrete means we are DTS, discrete time signal. So this case, what happens? It is followed by x of n. X of n is equal to a into cos of omega n plus pi. So that periodic condition. The periodic condition is followed by what we call x of n plus n is equal to a cos of omega n plus omega capital N plus pi. Okay, in this case where omega n, that omega n is, we know that it is specified 2 pi m, or we can consider that omega is the 2 pi m into n radians per cycle. So if it is integer m comma n. So for example, a discrete time signal, discrete time sinusoidal signal. Normally we know that discrete time signal, it is followed by what we call according to x of t, and here discrete time sinusoidal signal DTSS. Okay, this case where capital A is mentioned 1, pi equal to 0 and n is equal to 12. Okay, based on this all parameters, directly we have to specify this one, where n versus x of n. So like this, I have to verify this all a discrete time signal. This x of n versus time n. That x of n, here it is specified that, and second one, and third, and so on, discrete. Okay, the discrete levels are specified here from t versus t time n versus what we call discrete time signal x of n. Okay, like this, and what is specified here. Okay, these are all discrete time signals are specified. Time n versus what we call x of n. Yeah, this figure is followed by a discrete time sinusoidal signal. So normally we know the discrete time, where here the discrete time signal, but it is specified with reference to this discrete time sinusoidal signal DTSS. We will represent it graphically DTSS with the help of that mathematical notation. Based on this mathematical notation, user can specify this one. Discrete time sinusoidal signal is, it is specified a equal to 1, pi equal to 0, capital N equal to 12. Now after that we are going to verify that particular graphical representation, that figure, like this. Okay, this is followed by discrete time sinusoidal signal. Now coming to this sinusoidal or exponential signals. Yeah, it is specified in mathematical notation, where x of t is equal to a into sine 2 pi f naught into t plus pi. Okay, so a into sine of that 2 pi, that omega naught t plus pi. We have to simplify this one. X of t is equal to a into e power at, which is the real exponential. And if you want to that complex exponential, that x of t is equal to a into e power j omega naught t, it is also equal to A of what do you call cos of omega t plus j into sine omega naught t. It is a complex exponential. But real exponential, it is specified a into what do you call a into e power at. Okay, if it is complex exponential where x of t, that x of t is equal to what happens a into e power at. It is all our real exponential. Coming to the complex exponential, it is also equal to that what you call a into e power j omega naught t. It is also equal to that what you call a of cos what you call omega naught t, okay, plus complex no j sine omega naught t into omega naught t. Okay, it is specified in terms of this. Now it is considered where x of t is the continuous time signal is equal to a into cos omega naught t plus j into sine omega naught t. Okay, so it is all or nothing but exponential, complex exponential. Okay, so now, so where here the theta, we know that we are a phase of the sinusoidal wave, and A is also, we know that where capital A is the amplitude of the sinusoidal or exponential signal, where F naught we know the fundamental cyclic frequency of sinusoidal signal. Okay, where omega naught we know that radiant frequency, and what do you call, this is all nothing but a sinusoidal signal. The sinusoidal signal is mentioned mathematically, where x of t is equal to a into sine of 2 pi f naught into t plus theta. So coming to the elementary signal, we are entering that a step function, and a step function, it is followed by where t versus u of t, it is represented. So that step function, it is followed by u of t is equal to 1 t greater than or equal to 0, 0 t less than 0. Okay, using this all condition, we will expect this. Observe that step function like this. Next, coming to the shift a. Okay, here u of we know that step function, but it is shifted to a. U of it is followed by, so u of t minus a. Here using the same condition, 1 t. Here it is, they are using the 0. Here it is t greater than a. 0 t less than a. It is specified. Okay, now, so from t versus the unit shift is, it is shifted to t minus u of t minus a. Now it is shifted from here to here. So a here, this portion, it will appear the shift a. Okay, here u of t is equal to 1 t, that if it is u of t is equal to 1, if it is t greater than 0 of t equal to 0, 0 t less than 0. Using these all conditions, what happens here? The precise graph and commonly used graph. Okay, the precise graph is like this, t versus u of t, like this, and commonly used graph is what you call t versus, what you call, here it is specified the t versus, okay, the t versus what you call u of t. Okay, here it is of, no, here it is mentioned that of u of t, step function, here it is of here, and here it is 1. Okay, this is all unit step function. Next, signum function where t equal to, here this also we have seen previously, that signal function, how it is varies, where sine of t, and it is also equal to that 2 into u of t minus 1. This is the precise graph and commonly used for graph. The signal function is closely related to the unit step function. Using the solver, we have to consider the ramp. The ramp function is followed by t versus r of t. It is unit slope. The unit slope is where r of t is equal to what you call 1. The t greater than or equal to 0, 0, t less than 0. So the t of t is dr of t by dt, or concurrence r of t is equal to integral minus infinity to 1 u of tau into t tau, will represent it graphically. This is the simple operation with help of f of t, and f of t is equal to u of t minus r of t plus, like this. Next, come to the unit ramp function. This is the unit ramp function. It is specified. It is followed by RMP of t. Okay, where RMP of t is equal to t greater than 0, 0, t less than 0. Here it is integral minus infinity to t u of lambda into dt is equal to t into u of t. Okay, within this unit ramp function is the integral of the unit step function. So unit ramp function, it is specified that the unit ramp function is the integral of the unit step function. Here it is integral minus infinity to t versus into u of lambda into d lambda is equal to t into u of t. Graphically, you can represent like this. Okay. So it is called the unit ramp function because for positive t. Okay, it is slope is amplitude unit per time. It is specified unit ramp function. How this varies? The unit ramp function is an integral of the unit step function. It is called the unit ramp function because for what you call positive t. Slope is 1 amplitude unit per time. Okay, and this you have to consider rectangular pulse. The rectangular pulse is followed by the x of t is equal to a 0.5 minus 0.5 less than mod t less than 0.5, 0 otherwise. Okay, so we can represent that t versus the x of t. So like this, based on the 0.5, if you are there using that a here 0.5 plus 0.5 and minus 0.5. Okay, it is specified. Next x1 of t. So here minus 0.5, it is rectangular pulse is, it is specified like this. Okay, and the rectangular pulse are gate function. Based on this rectangular pulse, it is specified delta of a of t is equal to 1 by a into t mod t less than a by 2, 0. Okay, mod t greater than a by 2. Okay, so for this rectangular pulse will be appear like this. Okay, impulse function, you know, the under the elementary signals impulse functions, we have to observe this impulse function where t versus what you call x of t. Okay, so this area is specified here, area equal to 1. This area is specified 1. Here this area also area equal to 1. Like this 0 versus what you call this one, where t versus t of t impulse function, the strength is 1. Okay, if the strength is a, then the area equal to a, and so on. It is specified that impulse functions graphically and mathematically. Derivative of the impulse. So we can specify that derivatives of the impulse function. So here it is t. Here it is mentioned that, okay, and t, like here delta dash t and t if it is derivative of the impulse, it is specified r of t and u of t like this, and delta of t and delta dash of t if you are using the d by dt, derivative of the impulse function. Coming to the unit impulse function, as it approaches to 0, g of t approaches the unit step and g dash of is approaches unit impulse. Like this it is specified, g of t, t versus g of t. Okay, here this point is a by 2, this is minus a by 2, here it is off, here it is 1. As the approaches 0, the g of t approaches unit step, and if it is g dash approaches unit impulse. Here it is t versus g dash of t. Here it is specified a by 2. This is only minus a by 2. This is 1 by a. Okay, and so on. This is the functions that approach unit step and unit impulse. So unit impulse function is the derivative of the unit step function, or unit step function, or unit step is the integral of the unit impulse function. Okay, so unit impulse function is specified as it approaches 0, it is followed by 0 of t, approaches a unit step, and g dash of t approaches unit impulse. Based on this, so unit impulse function is the derivative of the unit step function, or you can consider unit step is the integral of the unit impulse function. So how they represent the impulse function in graphically or mathematically, you can consider the representation of the impulse function. The area under an impulse is called its strength or weight. So it is represented graphically by what you call vertical arrow. So an impulse with a strength of 1 is called unit impulse. As you can represent this based on the area, and if it is graphical by vertical arrow, an impulse width with a strength of 1 is called unit impulse. Like this it is specified, representation of the unit impulse, shift impulse of the amplitudes. Okay, what are the properties of impulse function? The sampling property, integral minus infinity to plus infinity g of t into delta of t minus t naught into dt is also equal to what you call g of t naught. Yeah, the scaling property, where delta of a into t minus t naught is equal to 1 by mod a delta of t minus t naught. It is the scaling property. Now come to the replication property. So where g of t with this, delta of t is equal to g of t. Come to the unit impulse train. The unit impulse train is the sum of the infinite uniformly specified impulses and is given by, so in mathematically it is followed by delta of t, capital T of small t is also equal to the summation where n is equal to initially what you call minus infinity to plus infinity delta of t minus n into t, where it is specified that n as an integer value. Okay, but here t versus the delta of t, so easily can specify that. Okay, it is specified the t versus delta of t, so where it is here the origin, here it is t, here it is t, here it is minus t, here it is 2t, here is 2t, here it is what you call, go on using the, here it is 3t, what you call 3t, and here also minus 2t and minus 3t and so on. So on, go on using that t is increases the time, how it is varies that are delta of t of t. delta of t is there. It is the unit impulse train is a sum of infinitely uniformly spaced impulses, and it is followed by what you call delta of t. T is equal to summation n equal to minus infinity to plus infinity. Delta of t minus n into capital T, where small n is an integer value. Okay, let this go on using this all out. T. Now rectangular, the unit rectangular function. Yeah, the unit rectangular or gate signal can be represented as a combination of the two shifted unit step signals like this. Rect of t, rectangular function. It is followed by RUCT of t is equal to u of t plus a minus u of t minus a. Okay, with this you can specify the t versus rect of t. Okay, so rect of t is equal to u of what do you call the rector. By using this all graphical representation, to verify that r rect rect of t is equal to what you call u of t plus a. Okay, is also u of t minus a. Okay, like this it is specified. We are coming to this unit triangular function. Yeah, triangular pulse whose height and area are both one, but its base width is not is called unit triangular function. Means the unit triangular is related to the unit rectangular and operation. It is called convolution. Okay, so like this, it is t versus the triangular function is specified the tri of t. Tri of t versus the t. It is specified that the triangular pulse whose height and area are both one, but its base width is not. It is called, you can consider unit triangular function. Yeah, the unit triangular is related to the unit rectangular through an operation called what you call convolution. So if you want to implement that convolution sum by using this MATLAB or other softwares, you can verify that graphically. For that we require convolution. Okay, next sometimes we require that sinc function. Sinc is for the SNC of t is equal to sine of pi t by t. Sinc is like this, t versus sinc of t. Okay, it is specified from this. Okay, now coming to this basic operation of signals, you know that operation performs and depending upon variables. Based on these variables, that we can decide the factors, amplitude, scaling, and addition, multiplication, and differentiation. This is the major operation performed on dependent variable. Yeah, if it is operations performed on independent variable, this is all dependent variable with the help of this amplitude, scale, addition, and multiplication and differentiation. Coming to this operation performed on the independent variable, so it is followed by time scaling, reflection, time shifting. Okay, from this, so time scaling, it is represented x of t versus t. Time scaling, here it is, what is the time scale? Here it is origin is 0. Okay, here it is 1. Here is minus 1. X of t versus what do you call the t. So what happens? The time scaling. The time scale is, it is performed here like this. It is specified x of t versus t. Coming to this, y of t is equal to x of 2t here. So this case, here it is, of origin is 0, of into t versus y of t Here it is specified where y of t is equal to x of into t. Like this, where x of n and y of n, it is specified in the time scaling. Okay, and reflection. So where x of t versus t, how it is reflected, this t1 to t2 and t1 to minus t2 and t2 to minus t1. Now it is reflected. What is it? Minus t1 to t2 is where x of t versus t is observed. Where y of t is equal to x of minus 2. Because of here it is time shifting. Okay, now since rule for the shift and the time scaling, there is a precedence where y of t is equal to x of a into t minus b, where where t is substituted 0, here it is what happens. So where y of t equal to 0 is equal to x of t equal to 0, no, a into 0 minus b. Okay, like this it is specified x of minus b. Okay, therefore if you want that x of 0, it is also equal to that y into b by a. This is the precedence rule for the time shifting and time scaling. Okay, so find this y of t is equal to x of 2t plus 3. Like here, that x of t versus t. Okay, so you can verify that graphically, and where x of t versus y of t, x of t plus 3. Okay, next y of t is equal to 2t, and like this it is specified. Now coming to the discrete time signals. Okay, like this, with elementary signals are depending upon this all variations and different parameters. Is that time scaling or maybe time shifting, ramp signal, and okay, where in terms of this continuous time signal or discrete time signal, how it is varies depending upon this time scaling properties. Okay, with this easily can specify that the continuous time signal is followed by x of t, where DTF discrete time signal is followed by x of x of n, like this. So this is all related to what we call elementary signals, like this. So I to use this one. These are all in terms of what we call elementary signal variation, how it is reflected with the mathematically and graphically. Okay, next we will see that distal signal details, discrete time signal, how it is varies, how it is reflected. Okay.
Like, share and subscribe. Hit the bell icon for more updates.